So we've obtained the fundamental solution for phi as well. Now let us look at a very important property between phi and psi. So let us consider an iso phi line. So for an iso phi line, d phi will be equal to 0, and that will be equal to del phi del x dx plus del phi del y dy. And if it is equal to 0, so del phi del x will be equal to u. So this becomes u dx. Del phi del y becomes v. This becomes v dy, and this is equal to 0. So if this is true, dy by dx for phi equal to constant, it comes out to be minus u upon v. And if you recall the condition for iso psi line, it came out as dy dx for psi equal to constant is equal to v upon u. And if you take the product of the two lines, dy dx phi equal to constant multiplied by dy dx psi equal to constant, that comes out to be minus 1. And this implies that iso psi lines and iso phi lines, well, they are orthogonal. I mean, my freehand diagram does not make it look entirely orthogonal, but they are orthogonal. The product of the two slopes at all the points will be equal to minus 1. So iso phi lines are orthogonal to iso psi line. So if you have iso psi lines like this, the iso phi lines will be something like this. Okay, and vice versa, and vice versa. So now, okay, fine. You've gone ahead and found out the solutions for either phi or psi. So you will find out the solution for phi when you have, in the given problem, if you have mass sources or sinks. If in a problem you have mass sources or sinks, you will make use of the fundamental solution for phi. If you have irrotational vortices in the flow, you will make use of the fundamental solution for psi, depending on the situation. So for example, if they say this is a domain where fluid comes out at the origin, then obviously you will write down the solution in terms of phi. You will write down the solution as m upon 2 pi log of r, where r is by definition square root of x square plus y square, because it's at the origin. So you found out the solution for phi and psi somehow, and now the question is, how do you find out the variable which we have not discussed so far, that is pressure? Once you found out phi or psi, by making use of the definitions of velocity, like for the case of phi it is del phi by del x, v equal to del phi by del y. For the case of psi, u is minus del psi, rather u is del psi del y, v is minus del psi del x. Making use of these definitions, you will find out the velocity components. Once you find out the velocity components, you know that you are in a domain which is inviscid and irrotational. So between any 2 points, you can apply the Bernoulli theorem, because you are in a domain where you not only do not have the influence of viscosity, but you are also sitting in an irrotational domain. So you can apply P plus half rho mod u square, where mod u is like the magnitude of velocity. Mod u will be, so mod u vector. Okay, so mod u vector will be the square root of u square plus v square. So P plus half rho mod u square will be equal to P infinity plus half rho u infinity square, where this is like some far stream boundary condition. So all this would be very much clear by means of examples, but all you need to remember is that in the domain you can make use of p plus half rho mod u square plus rho gz. Usually you are all sitting in a single plane. All these are two-dimensional flows. So the influence of z is typically not required because you are only having two dimensions, and this will be constant. All right.